the number of moles of carbon monoxide at equilibrium. Equilibrium moles of carbon monoxide, 6 moles. Our change, delta N equals N final minus N initial. The final number of moles is the 6, initial number of moles 0, so 6 minus 0 will give us positive 6. Like I always say, make sure you put the sign of the change, whether it's positively changing or negatively changing. Right? We now have the change of one substance. With that change of one substance together with the ratio, we can determine the change of the other substance, which in this case is carbon dioxide. The ratio is 2:1, 1 being half of 2. Whatever comes here as the change of carbon dioxide has to be half of 6. So it's going to be -3. It's a reactant that is changing negatively. Once you get a positive change on this side of the products, on the reactant, it has to be a negative change. Right? Equilibrium number of moles of carbon dioxide, X minus 3. We just write it as X minus 3. Then we move on to the concentration at equilibrium, where we now have to divide the equilibrium moles by the volume, which is given as 2. X minus 3 divided by 2. We keep it like that. We cannot further simplify it. We leave it like that. 6 divided by 2, we get 3 moles per cubic decimeters. Okay. These are the concentrations at equilibrium. From there, we now move on to the Kc expression. Let me just write this. Kc, concentration of the products. We have only one product, carbon monoxide. So CO square brackets. The square brackets means concentration in the context of chemistry. Divided by, we have 2 reactants, but one of the reactant, like we indicated earlier, or I indicated earlier, is in solid state. It cannot be included in the Kc expression. So we are going to only consider carbon dioxide, CO2. That is our Kc expression. Kc value is given, it's 14. So we substitute 14 equals the concentration of carbon monoxide 3 squared divided by, right. Let me, instead of writing the CO2 like what you want me to do, let me write it as X minus 3 divided by 2. You see, we now have a fraction within a fraction, which might give you serious problems with simplifying. So you just have to consider the carbon dioxide concentration instead of substituting this fraction. Okay? We multiply both sides by the concentration of carbon dioxide. This goes, remain with 14 multiplied by the equals 9. Divide both sides by 14. Our concentration of carbon dioxide is 0.642. One person at a time. I can David.
0.642.
0.642 moles per cubic decimeter. So we now have the concentration of carbon dioxide from this calculation. But here in the table, we also have the concentration of carbon dioxide as X minus 3 over 2. So I can equate the X minus 3 over 2